So now that we've looked at the properties, the mean and the variance of a Poisson distribution, today we're going to look at the mean and the variance of the binomial distribution. The mean, or the expectation, we already found this. This is a technique I asked you to use when we were conducting a hypothesis test. We found the expectation, and that gave us some information on which tail we wanted to focus on. Well, we can do more with the expectation. But as a reminder, when finding the expectation, we first need to get the distribution. So looking along here, we have 200 people. We're checking to see whether or not they're left-handed. The probability of being left-handed is 0.1. So the distribution is x follows a binomial of 200 and 0.1. How many of these 200 people do we expect to be left-handed? The expectation is going to come from n multiplied by p, the number of trials multiplied by the probability. 200 times 0.1, we would expect 20 of these people to be left-handed. So the expectation, we've been finding that already. Let's focus on the variance. There is the proof from first principles, which we won't spend any time on now, but later on in your course, you'll be able to look back and you'll realize how to conduct that proof. But simply put, if you have a distribution, a binomial distribution with the parameters n and p, the expectation is going to be np, or the mean is np, whereas the variance is going to be npq. And I hope you can see that the standard deviation will be the square root of the variance, so the square root of npq. If you notice here, I'm referring to npq, where q is the probability of failure. But sometimes you will see this written as NP 1 minus P. Both of them are valid. The NPQ is just easier to work with. You can quickly do a mental calculation to find Q if you know P, and to find P if you know Q. The NP 1 minus P form, that also has its own benefits. Sometimes you might need to produce a quadratic equation. You can see expanding this bracket will give you a quadratic which you might be able to solve. So both of them are valid. I have a preference for NPQ. Okay, let's see this in action. You may well get some questions that are going to ask you to find the mean, to find the variance, but not just simply to find them, to actually use them in some sort of context or calculation. Okay, let's go through some examples. So in this first one, we're told that a fair four-sided die has the numbers 1, 2, 3, and 4 on each of its faces. The die is to be rolled 20 times, and the random variable x represents the number of 4s obtained. We're asked to find the mean and the variance of x. The first thing I want to do is actually to write out the distribution of x to begin with. It's going to be a binomial. There were 20 fixed trials, and we're looking for the number of 4s obtained. The probability of getting a 4 is a quarter, 0.25. The expectation from here, n multiplied by p, 20 multiplied by a quarter. I'm sure you can all do this in your head. That gives us 5. The variance, sigma squared is the variance. That's going to be n times p times q. Well, I already know that np is 5, so I'm just going to do 5 multiplied by, well, q is the complement of 0.25, so it's 0.75. So when we multiply these, we get 3.75 for our variance. So that's part A, quite straightforward, just asked us to find those two things using the formulae we've just looked at. Part B asks us to find the probability that x is less than mu minus sigma. Mu is the mean. Mu is the expectation of x. We found both of these values. Well, we found sigma squared. We can easily find sigma. It's going to be the square root of 3.75. So the probability that x is less than mu minus sigma is actually the probability x is less than 5 minus 1.936. That's x being less than 3.064. And we know that x has to take whole numbers for a discrete distribution like the binomial. So we're actually calculating the probability x is less than or equal to 3. We can do a BCD calculation and we get our answer, 0.2252. So really just ensuring your understanding of how to calculate the mean and the variance and your familiarity with these symbols that we've been using. Mu, maybe it's a bit new to you, is the expectation of x. Sigma is the standard deviation. Sigma squared, well, that's your variance. Okay, so in this second one, we're told that David believes 35% of people in a certain town will vote for him in the next election, and he commissions a survey. We've been asked to find the minimum number of people the survey should ask to have a mean number of more than 100 voting for David. So let's start with this last statement. We want a mean number of more than 100 voting for David. Well, we know the mean is synonymous with the expectation. So we actually want the expectation to be more than 100, which means that NP should be more than 100. We know what P is, we don't know what N is. That's what the question actually wants us to find. So 0.35N is greater than 100. N must be more than 100 divided by 0.35. Doing that division, we get 285.7. Well, we needed to know the minimum number, and since N must be an integer and must be greater than 285.7, we'll choose 286. David is going to need 286 people in the survey to give him a mean that is bigger than 100. So this question, just making sure you're actually reading, processing, understanding that the mean is synonymous with the expectation, and then working with the inequality and setting it greater to 100. So a little bit more context-based and application needed from you for that question. Let's just do one more. So in this one, we're told that an examiner is trying to design a multiple choice test. For students answering the test at random, he wants the mean score on the test to be 20 and the standard deviation to be at least 4. We're asked to find how many choices he should make for each question. So question 1, is it going to have option A, B, and C, or option A, B, C, D, E, F, and G? How many options should they have for each question? We're told that the number of choices is to be fixed across all of the questions. So that's going to be constant, and it should be as small as possible. So the number of choices is actually going to match directly to the probability of someone at random answering correctly. If there are only 2 choices, well, they have a 50-50 chance of being correct. 0.5, 1/2 is the probability they'll be correct. If there were 3 choices, the probability they randomly pick and are correct is 1/3. If there's 10 choices, the probability they randomly pick and are correct is 1/10. So that probability is directly linked to the number of choices. Let's make a start. We're told that the mean of the test should be 20. So the expectation, which is NP, that should be equal to 20. There's not much I can do with that right now. We're also told that the standard deviation should be at least 4. So this includes 4. I can say that sigma is greater than or equal to 4. Sigma squared is greater than or equal to 16. Okay, sigma squared, we do have a formula for that involving NPQ. So I can say that NPQ should be greater than or equal to 16. Well, NP, we already have a value for NP, that's 20. Rewrite this, 20Q is greater than or equal to 16. Q, the probability of getting a question wrong, should be greater than or equal to 16 over 20, 4/5. So Q is set at 4/5. We know that P is the complement of Q. So P equals 1/5. The probability of someone guessing at random and being correct is 1/5, meaning there must be 5 choices to the question. 5 choices for each of these multiple choice questions. Now we've got a value for P, can we go back and find a value for N? Well, NP equals 20, so 1/5 of N equals 20. N should be 100. We found both of these two things. The number of choices or options per question should be 5, and the number of actual questions that are asked should be 100. Okay, so just expect problem solving to appear regularly. Now that we know NP and NPQ, we should be able to be quite creative with the questions we can respond to. You have to get involved in the context. Here, the thought process of how many choices are in the multiple choice question led directly to interpreting the value of P. The value of P linked to the number of choices. So I just want to stress, what do each of these parameters actually mean? Keep track of N. N is the number of trials. Keep track of P. That's the probability of success. And keep track of Q. That's the probability of failure. It's your job to interpret and model from the context to the mathematical model and then back again.